Um, so that you don't need to scribble all these notes down. You can always take your time and look back on it, okay? Because these notes will appear on the website afterwards, as usual. What I want to look at today is to point out to you where the video lectures are that I said that I would put on for each of these circuits. Now, how the heck do you spell across? Is it two C's? That's fine. Good. No, that's an R there, that little thing before the O. Yeah. So there are video lectures for step voltage put across a resistor and an inductor in series, and a resistor and a capacitor put in series. And also there are video lectures for separately, one for a resistor and a capacitor, and another one for a resistor and inductor. And they last about 7 or 8 minutes, something like that. So have a look at those. And again, on SharePoint, the videos are there, as well as the notes, so you can print those out. But on YouTube, I've put the videos, however, you can't upload the notes. So SharePoint is probably the best place to go if you can get there. Yeah, yeah. So that's this. When you come to the assignment, which I'm going to be discussing today, is these circuits. When you come to the assignment to do towards the good pass. So pass, good passes. These two circuits. If you want to go a bit further, then there's the ramp voltage put across a resistor and the capacitor, which is the merit. The extent, the resistor and inductor, we're not going to particularly focusing on this time round. So if you want to look at that, that's an extension activity. Yes, there's an exam, but the assignment is particularly what this is focused on today. Okay. So that's one thing I want to look at, show you where they are. I want to look then at, which is the bulk of today, this particular circuit, the inductor, capacitor, and resistor. I want to use Laplace transforms to analyze a couple of circuits. We'll look at one together, then you'll have a go at one, and then we'll look at a case where we would get critical damping, and we can at that point discuss with Mike's help maybe what the effect of over and under damping is in these circuits. So by the end I hope we'll understand those. And then finally just talk a little bit more about the assignment, what's coming up. So that's the plan. Okay. Okay. Let me show you where these lectures are. If you go to SharePoint, you'll see the lectures there. Now I've gone to the page where they all are, but if I were to just expand this out, you'll see where it is. So if you go to the student SharePoint, hopefully you can all get to SharePoint and log on. If not, then you're stumped already at the first step. But as long as you can get there, then you go to the higher education. You don't need to jot this all down. If you're watching this video, you see it, but then of course you need to be up to SharePoint to actually get to the video. So yeah, so you go to SharePoint, and then you go to higher education, and once you're in there, you go to HE engineering. Once you're there, you go to the BEng and Foundation Science and Engineering Operations on the right hand side, and then Mike's unit, Electrical and Electronic Principles, and in there you'll see the video notes on the Laplace transforms. Okay, so that's the way to find them, and that's probably the best place to go to get it. Okay. Once you're there, then you'll see this. You'll see the PDF bars for the notes and the videos. Earlier ones that we had where we introduced the Laplace transforms, looked at some simple networks are there, but the ones I really want to focus on are these 3 or 4 here, look. Step voltage across an inductor and then a capacitor, 2 together in this one. And then there's another one, part 2 on the voltage across a capacitor. And then the ramp voltage across the inductor, which is the extension exercise. And then some further questions to have a look at to practice those. Okay. What's going on here? 1 to 15, are there some extra ones? All right, that's Yeah, on page 15, that's where the other parts are. Look. There may be an error in something on there because when I worked out the answer at the end, I couldn't quite believe what it was, but I'll put it on anyway. So if you can find out where the error was in there, I'm not sure there is, but you'll see it when you see it anyway. Okay. Right, so those are the video links that you can have a look at. And I'll put this one we're looking at today in there as well. Happy? Right, let's close that down then. So today I want to look at this circuit then. Don't bother to write all this down. This is by way of introduction. We've already looked at it. The general solution for the current flowing through an LCR circuit is formed from this, the solution to this. And if you remember when we first introduced this, I gave you this or a second order differential equation, which is what we have to solve and what we use the Laplace transforms to solve to analyze this circuit here. Do you remember us talking about voltage? You should be familiar with this. Voltage across an inductor is the inductance times the rate of change of current, which is this bit. The voltage across a resistor is just Ohm's law, which is this bit. And the voltage across a capacitor is given by this, which is this bit. So this gives us the differential equation, which we solve. And we end up with this beauty, okay, which is the general solution. If I want to know what the current is, I, at any time t, I just plug the numbers into this formula here. And we'll look a bit later on at this on autograph and see what it looks like. In other words, if I've got a voltage E, an inductor L, I can calculate the current at any time. R for resistance, L for inductance. So it's to do with the inductance, the values for the inductance of the capacitance and the resistance in this circuit. I change any of these values, it's going to affect what happens in this circuit. So the beauty of this is, if I then have got this formula, and this is the whole point of doing it, I can put in some values for the resistance, the inductance, capacitance, and work out how it will behave. What's the effect of changing resistance? What effect does it have on the circuit? And then we start thinking about things like, at what point do I get critical damping, which is actually the ideal, what we're looking for. Is it going to give me an underdamped or an overdamped situation in this circuit? And by looking at this formula, I can analyze the circuit. What we're going to do, though, is just initially focus on using the Laplace transforms to come up with a value for the current, given some values for the inductance. But this is the general form. So that's an introduction. Let's have a look at an example now and use our ideas of Laplace transforms and analyze this. So if you would like to just make a note of this. So I want to come up with an expression for the current. I equals E over Z. So as before, we transform E and Z into S space and then put them into Ohm's law. Fiddle around with the I in S space to get it into a form where we can then transform it back to time or into the normal world effectively, and then we should be able to match it up with one of these things on here. So that's the plan. I should have made it plain, of course, that this is a step voltage of 10 volts. So you've got your table of transforms in front of you. What's the transform for the voltage? Ten over S, thank you. Now, what about the total impedance? Just jot down what you think the total impedance is. So we'd have resistance of 1, the inductance would be 100 S, and the capacitance would be 1 over 0.1 S. Agreed? Now, a little bit of algebra now, just to sort of help to tidy this up. First of all, yeah. Okay, so just a little bit to tidy this up. 1 divided by 0.1, if I multiply top and bottom by 10, 1 divided by 0.1 is the same as 10 over 1. So I would instantly get rid of this 0.1 underneath and call this 1 plus 100s plus 10 over s, to try and make life a little bit easier for myself. Okay, that's something we can always do. You can always get rid of a decimal point on the bottom in any fraction by multiplying top and bottom by 10 as many times as you need to get a whole number on the bottom. Makes life a lot easier for yourself. Now, for reasons which will become apparent, this is another good idea. I want to rewrite all of these over s. If I write this one as 1 times s, or s over s, that's 1, isn't it? S divided by s is 1. Agreed, Mark? How would I rewrite this so that it was over s? What would this have to become? If I want to divide s squared, because if I cancel the s, yeah. Never be worried about being wrong, Jamie. And there's a reason for doing that. Because they're all over s, I can not get rid of them, or I can just write them all over s. Okay? Plus 100s squared plus 10 all over s. And that is a convenient way to write the total impedance in s space. We could have done that before when we had problems where we were trying to combine things. But now it's actually quite handy to do it that way. That's not to say we don't need to do that. We could have solved this without, but it makes life a lot easier. So now, put these into Ohm's law. I s equals E over Z, doesn't it? Okay, that's Ohm's law written in S space. But don't forget, dividing by the total impedance is the same as multiplying by 1 over the total impedance. There's a reason why I want to think of this like this. Okay. So the reason why I want to think of this like this is because if you look at Z, which is this Z, I can find out what the inverse of Z is, 1 over Z, by inverting it. So if I invert Z to get 1 over Z, I would invert this. So I can write, and that's the reason why I wrote, why won't that go there? The reason why I wrote this in this form was so that I could invert it. So I can write that 1 over Z equals S over S squared plus, S plus 100S squared plus 10. Therefore, IS equals ES, which is 10 over S, multiplied by S over S plus 100S squared plus 10. And again, I'll just pause while you make... Okay. Oh, look! They cancel, okay? So, IS equals 10 over S plus 100 s squared plus 10. Right, now we want to transform this back to t. Is there anything on our table, page 5, that looks like any of them?
Yes.
Which one, Nigel? It looks a little bit like it, that's true, but it doesn't look exactly like it, does it? What have we got? Yeah, it looks like, yeah, do you remember what did we do to try and get this to look like that? Right, we used the method of perfect square, didn't we? That's what we got to do now. So, let's have a look at this. First of all, let's rewrite this so that IS equals 10 over. Now, let's write it so that we've got the 100 s squared first, plus the s plus the 10. The more familiar form for the quadratic, okay? Now, when we use the perfect square method, all the ones that we did had s squared on its own. So the fact that it's 100 s squared is a problem. What can we do to get rid of that 100? Divide by 100. Right, Jamie. Is that, sorry, I thought that's what you said. Divide by 100, it's gone, isn't it? If I divide that by 100, what else have I got to do? Divide every term by 100. So divide every term by 100, and we've not changed it. But we've got rid of the 100 in front of the s squared, which is what we want to do. Divide 10 by 100, 0.1. Divide 100 s squared by 100, s squared. Divide s by 100, 0.01 s. Divide 10 by 100, 0.1. Because the perfect square method that we used at the beginning always had s squared on its own.
Now we can make that into a
Yes. Can you remember what we do to make this into a perfect square?
square.
Yeah. No, for the perfect square method, we half this, don't we? Do you remember? Half of that. So this equals 0.1 over s plus, what's a half of 0.01? 0.005 squared. Now, what have we got to do about the rest of it? What have we got to do now, though? Square the 0.005. What's that? Okay, so effectively now we've got to take that away from the 0.1, haven't we? So 0.1, take away whatever that answer is, and we get 25 times 10 to the minus 6. Or 0.025 times 10 to the minus 3, or that's not right. So to get to this point, we've halved the coefficient of s, which is 0.01, to get 0.005. And to find out what's left, we square the 0.005, because that's the perfect square bit, and take that away from 0.1 to see what's left. Okay? And then round the answer and we get this. Everybody happy with that? So how do we get this? What do we do? How do we get this? Let's put this into words.
Square the 0.05.
So how do we get, right, so we square 0.05, 0.005, yeah.
And then minus that from the original 0.1.
And subtract from 0.1. Okay. No, the 0.1 here, yeah. Yeah. Look at the table of Laplace transforms, page 5, and you'll see we've got the damped sine wave. So now we can transfer back. Using AE, I'll get these symbols the right way around this time, sine omega t, the damped sine wave in other words, transforms to A omega over S plus B all squared plus omega squared. The only thing we've got left to do is find A, isn't it? We now know we can write down what B is and what omega is. What's A? So therefore A equals 1, B equals 0.005 and omega equals 0.1. We put the figures into the transform. We get I, the current, then is described by this function. E to the minus 0.005t sine 0.1t. If this is what you'd come up with and you had to go at one of these in the assignment, then you'd put this into autograph and see what it looked like. And then you'd build a circuit with those components in and look at the circuit, an oscilloscope trace for the circuit, and compare them. This is modeling what we'd expect the circuit, how we'd expect the circuit to behave during its transient period before it settles down to a steady current. If we put a step voltage across here and we go back to the original, this one, step voltage with a capacitor in the circuit, what would you expect the current to settle down to? Yeah, and then a steady 10 volts, yeah. Yeah, right, because the capacitor will eventually become charged, so eventually it will come to zero, okay? But what's happening during that transient period, the instant you turn it on before it settles down? So, let's have a look. So if we go to autograph and type in the function, so as a reminder, fire up autograph, hit equals, and then type in the equation, or the formula rather, using y for the current and x for time. So we were going to type in y equals e to the power, which is that hat symbol above the 6, minus 0.005x, that's the decay part of the circuit, sine omega, which is 0.1x. And then hit OK, and we get the circuit. No, we don't. What's going on here? Probably because I didn't put a bracket around the 0.01x. So let's try that. Anything else I've done wrong? I don't think so. No. So let's zoom. Let's see what's going on here. Let's zoom out on the x-axis. Ah, here we go. No. Yeah. So it's looking a bit like this during this transient period. So let's zoom in on the y-axis. Zoom them out a bit on the x-axis. Remembering these things, we're only interested in what happens to the circuit after time equals 0. So this is very, very undamped. Okay, it's oscillating over time before it eventually will settle down to a steady to 0. Okay. The fact that this is 0.005 means that it's going to take a long time for this thing to settle down. So for a small value for this power here, because we're multiplying the time by 0.005, so exponentially it's going to change very slowly. Okay, so if I built a circuit like that, it would take ages to settle down. Look, time here, 100 seconds, 200 seconds. It's going to take a long time for this current to settle down to 0. Right, I'll put that into the notes. While I'm doing that, though, I'd like you to have a go at one. So, okay, try this circuit. We've got 10 ohms in series with a 0.1 Henry inductor and a 10 microfarad capacitor. So go through the same steps. You're going to get some awkward figures this time, but follow the same algebraic steps. So hopefully with a little bit of jiggery pokery and thinking about what's going on, we can use a calculator here. What's 1 divided by 10 times 10 to the minus 6 is 10 to the 5, but think about what it means. 10 times 10 to the minus 6 is 10 to the minus 5, and the inverse of the inverse is 10 to the 5. So 10 to the 5 over s, multiplying everything, these two by s, and we've got a common denominator, that's all over s. So we get zs equals that. And then we carry on from there, okay? So if I just leave you for a minute or two to carry from that point. So I can write 1 over z is that, and then I can plug them in to get the current. IS equals effectively 10 over, because the s is cancelled. Now multiply everything by 10 to get rid of the 0.1 in front of the s squared, and you're away. This gets us to here. Now we want to form the perfect square. So to get the perfect square now, half of that 100 is 50. So IS is going to equal 100 over s plus 50 squared, and now I've got to work out what this omega squared is. Plus, so 50 squared is whatever that is, 2,500. A million minus 2,500 is 997,000 something like that. What's it? Oh, no.
9997.
997,500 because I've taken 2,500 out. Yeah. Okay. So, oh, might be fading out a bit here. Forgot to put this on. Never mind. So, omega squared is that.
I think it's 997.
Yeah. No, that's right. That's right. Yeah. Yeah.
Well, so you're doing 50 squared, yeah.
Now we know that omega squared is that. So we can find omega. We know that B equals 50. All that leaves us to do is to find A. So if you could just do that for me.
You've still got 10 to the 6.
So with those figures, we can write that IT equals. Okay, so A equal to 0.1, eventually rounded to that. We can now put our figures in here. So we can say that the current equals A, which is 0.1, e to the minus B, isn't it? Yeah, B, which is 50. So we're going to get this thing decaying a bit more rapidly this time because B is quite large. Sine omega, which is, what's omega? 998.7T. Okay. Right. Let's just think about this. I'm not going to put this in the autograph, you are, but let's think about it. Okay. And to focus on that in a minute. Okay. Let's just listen to here. So 50, large number in there means it's a fast damp rate. Yeah. Okay. Large omega means, remember what omega is? High frequency, yeah. So you're going to get high frequency oscillation damping away very quickly. As a little extra exercise, you could plug this into autograph and see what that looks like. Okay? Now, I want to just give you one more to have a look at, but I want to take this away because I'm going to give you some conditions now which will lead to critical damping. So what I want you to do for next time I see you is to tell me what's going on to give me critical damping. And when you go through it, you'll see why. So, L equals the inductance 0.1 henries. The capacitance is 0.001 farads, and the resistance is 20 ohms. What I'd like you to do, again, the voltage E, 10 volts, although that actually doesn't matter what the voltage is because we're looking at a critical damping situation. So for those values, I want you to calculate the function. Okay.
Still the same,
Yeah, same step voltage of 10 volts, same circuit. Yeah, LCR in series. Yeah. Okay.